Hello, everyone, to this week's Symmetry Seminar. It's a pleasure to have Luisa, who will be telling us about dualities between 2D fusion surface models from braided fusion categories. So please go ahead, Luisa.
Okay, thanks for the introduction. So yeah, my talk today will be about dualities between a class of two-dimensional quantum lattice models that were constructed from braided fusion categories. And my talk will be based on my recent arXiv preprint, but I'll also include some results from an earlier paper with Paul Fendley. Okay, so let me start by clarifying what I mean by duality. So two Hamiltonians are dual when they can be decomposed as a sum over local terms, such that these local terms generate the same algebra. And the key consequence of this is that the Hamiltonians will then have the same energy levels in their spectra, up to some subtleties with boundary conditions, but the degeneracies of these energy levels can be different. In particular, we expect that the energy gap in the thermodynamic limit is preserved. So if one Hamiltonian is gapless, its dual Hamiltonians should also be gapless. And examples of this type of duality include the Kramers-Mané duality, of course, but also more general dualities that map between models defined on different Hilbert spaces, for example, by gauging discrete symmetries or orbifolding. And in modern terminology, these types of dualities are often called bond algebraic dualities, but I would say that the idea behind it goes back to much earlier work by Temperley and Lieb and Baxter. Okay, so one motivation for me to study these dualities was that they fit very naturally into the anion chain framework. I will give you the details later, but for now, here's the big picture. So it is well known that starting from a fusion category, we can construct a one-dimensional quantum lattice model known as the anion chain, which inherits the categorical symmetries of my input category. Later, it was understood that we can refine the input by the choice of a module category over the fusion category. I will explain what this is later on, but you might have encountered this mathematical structure before in the context of gap boundary conditions of topological orders. So anion chains constructed from different module categories over the same fusion category turn out to be dual. And in fact, we can write down an operator mapping between these two models. So the main goal of my talk will be to discuss how we can extend this framework to one dimension higher. Recently, Kansai Nomura and Kantaro Omori introduced fusion surface models, a class of 2D quantum lattice models, which generalize the standard anion chain construction. In order to construct these, the minimum thing we need to do is we need to add braiding to the fusion category. Then taking a braided fusion category as an input, we can get quantum lattice models which have one-form symmetries corresponding to objects in B. So this naturally raises the question, can we apply a similar strategy as in 1D and refine the input in order to find dual fusion surface models? And the short answer is yes. This indeed works using a structure called a module tensor category, and I will give you the long answer in my talk. Okay, so here's the plan for today. I will start with reviewing dualities between anion chains, followed by a quick introduction to fusion surface models. Then I'll move on to the main result, which is how we can construct these dual fusion surface models. After that, I will do two sets of examples, one based on the REP-S3 category, which will provide a way to write the XXC honeycomb model as a fusion surface model. The other set of examples is based on copies of the Ising category, and there we will find a bilayer guitar honeycomb model with an interesting phase diagram. And in the end, I will say a few words about the fusion 2 category symmetry of these generalized fusion surface models. Okay. So for my talk, I will need two mathematical concepts, fusion categories and module categories. Most of you are probably familiar with fusion categories. These consist of a collection of objects that I will denote by Greek letters, along with some fusion rules. In the graphical calculus, the lines in the graph are labeled by objects in the fusion category, and I can draw a trivalent vertex like this if this fusion coefficient here is equal to 1. I will only work with multiplicity-free fusion categories here, so this coefficient will always be 0 or 1. The data of the fusion category also includes F symbols, which allow me to relate the graph on the left to the sum over graphs on the right. Now, a module category over this fusion category consists of a different set of objects that I denote by capital Arabic letters. The fusion category has an action on this module category. This means that there's a product between objects in the module category and objects in the fusion category, which gives me a sum over objects in the module category. And pictorially, this corresponds to a trivalent vertex where two objects of the module category meet one object in the fusion category. And now this fusion coefficient here can be greater than 1, meaning that the fusion space can be multidimensional. And so this trivalent vertex can additionally be labeled by basis vectors spanning this potentially multidimensional fusion space. Just as the fusion category has F symbols, the module category has its own set of module F symbols. And to give an example, so any fusion category can be regarded as a module category over itself. That's sometimes also called a regular module category. Also, when the fusion category is of the form rep G, then any rep H, where H is a subgroup of G, makes a module category over C. Okay, so then the regular anyon chain construction starts with a fusion category and a fixed object, and the states in the Hilbert space correspond to these types of fusion trees, where all the vertical legs are labeled by the fixed object rho. The horizontal edges carry the dynamical degrees of freedom, which take values in the fusion category. And because the fusion rules have to be satisfied at these vertices here, the Hilbert space can be constrained. In this kind of like extended anyon chain framework, we also choose a module category over the fusion category as input. Then the horizontal edges are labeled by objects in the module category. And as I've said before, we can also have additional degrees of freedom labeling the basis vector sitting at these trivalent vertices. So basically changing the module category changes the degrees of freedom in our Hilbert space. The Hamiltonian can be represented by fusing a line labeled by an object in the fusion category to these fusion trees. This diagram can be evaluated using the module F symbols, and it gives me an operator which changes this middle horizontal edge, and it also can change the state of these trivalent vertices, but it's acting only diagonally on the left and on the right horizontal edge. Symmetries are represented by fusing lines to the fusion tree from above, and the intuition is that these commute with the Hamiltonian, which is acting from below. So the symmetries are labeled by objects in the so-called Morita dual fusion category. By definition, this category set has the same Drinfeld center as C. And the action can be found explicitly using yet another set of F symbols, sometimes called bimodule F symbols. Now, in the regular case, when the module category is just the same as the fusion category, the symmetries correspond to objects in C, and all these different F symbols just reduce to the standard ones. Okay, so to be a bit more concrete, I'll do an example, which I will later redo in one dimension higher. So the example is based on the rep S3 or SO3 level 2 fusion category. This category has 3 objects, and I will denote the non-abelian object by 1, because its fusion rule is reminiscent of a spin 1 type object. There's also an abelian object 2, and then the identity object 0. To label the vertical legs, we will pick the non-abelian object. So then the regular anyon chain has states which look like this, and it turns out that this Hilbert space is constrained. So for example, if we have this horizontal edge labeled by the abelian object 2, then because of the fusion rules, the edges next to it have to be labeled by the state 1. So this gives me a constraint on the Hilbert space. And something similar applies to having the identity object here, so this also has to be surrounded by 1s. But actually, there's a nice physical interpretation of this constraint in terms of Rydberg blockade atoms. These atoms can be thought of as having two states, a ground state and an excited state. And there are strong van der Waals forces which prevent the simultaneous excitation of two atoms within a certain blockade radius. So now you can picture a square ladder of these atoms and let the state 0, 0 and 2 correspond to having an excited atom on the top or an excited atom on the bottom. And the state 1 here means that the rung has no excited atoms. Then this categorical constraint translates into the blockade constraint that if this atom is excited, then the atoms in a certain disk around it can't be excited at the same time. Yeah, so that's just like an illustration that sometimes these constrained Hilbert spaces can also have like physical interpretations. Now, if instead we choose a different module category, in particular here the trivial module category back, then we get a very simple Hilbert space of qubits. And this is because the horizontal edges are now all labeled by the unique object in back. So this doesn't really contribute degrees of freedom, but we have the 2 degrees of freedom sitting on these trivalent vertices here because the fusion space here is 2-dimensional. For the Hamiltonian, I choose this particular form where the S operator corresponds to fusing the non-abelian line of the REP-S3 category to the fusion tree, and the operator P corresponds to a sum over fusing the abelian lines. Then for any choice of a module category, these local terms generate a bond algebra known as the SO3 BMW algebra. So that's just one example of a certain bond algebra. And in particular, if you take the trivial module category, this Hamiltonian here is nothing but the well-known spin 1/2 XXC chain Hamiltonian. The S operator contains all the off-diagonal terms in the XXC chain, and the P operator corresponds to the diagonal ZZ interaction plus an identity constant. I could also write down the operator for the Hamiltonian for the Rydberg ladder, but I'm not doing it here simply because it takes more space to write it down. Now, from this whole construction, we can get two main payoffs. So the first payoff is that we know the symmetries immediately. The Rydberg blockade ladder has a REP-S3 symmetry, which is generated by an invertible Z2 symmetry corresponding to the abelian object, as well as a non-invertible symmetry corresponding to the non-abelian object. The XXC chain, on the other hand, has an S3, a finite S3 symmetry, which is Morita dual to the REP-S3 symmetry of the Rydberg blockade ladder. The second payoff is that we know their phase diagrams will be related because of the duality. So in particular, we all know that the XXC chain is critical when delta is between -1 and 1. And so we can infer that the Rydberg blockade ladder should also be critical in this regime. However, as you can see, the conformal-Fleet theory describing these critical regimes is not quite the same. They are related by orbifolding, and also in the gap phases, the number of ground states is different. So the two models I would say they don't really have the same, so they are related by this duality, but still they can have different gap phases and also different conformal-Fleet theories. Okay. So now I will briefly give you some details on the fusion surface model construction, because we will need this in order to understand the dual fusion surface models. So the original proposal used fusion 2 categories as input, which means that then surfaces have to be introduced into this graphical calculus. The reciting models then have 0 form and 1 form symmetries. However, in my talk and in my papers, I make the simplification that I only take braided fusion 1 categories as input, in which case we don't have any labels on the surfaces, and the lines are labeled by objects in this braided fusion 1 category as before. One practical reason for doing the simplification is that we barely know any fusion 2 category for which all the skeletal data has been worked out. And without the skeletal data, we can't really write on the Hamiltonian explicitly. Okay, so then starting from this braided fusion category, the states in the Hilbert space could now correspond to diagrams like this. As before, all these vertical blue legs are labeled by a fixed object rho in my braided fusion category, while the planar black edges carry the degrees of freedom spanning my quantum state. I've made a distinction here between gamma I and gamma ijk, but that's purely for geometric reasons, because this ijk edge here is surrounded by edges I, j, and k. So there's no deeper distinction between these two. Then for the Hamiltonian, I choose this particular form. So the last term, the jz term, is just the same as the local anyon chain Hamiltonian, but the jx and jy terms are a bit different because they couple more degrees of freedom and they involve a crossing between this blue line with the black line. So that's where the braiding comes in. In order to evaluate those, we need both the F symbols and the R symbols of the braided fusion category. Typically, this R symbol is going to be complex, and so the Hamiltonian might not be real, which means that there's a good chance it breaks time reversal symmetry explicitly. By design, the Hamiltonian conserves a one-form symmetries corresponding to objects in B, which show up as mutually commuting plaquette operators, as well as string operators acting on incontractable cycles if the system is defined on a torus. Okay, so for me, the key example of a fusion surface model is Kitaev's honeycomb model, which can be written as a fusion surface model constructed from the Ising category. I will also need this example later on in the context of dualities, so that's why I will go over it here. So the Ising category has three objects, and in these pictures for the states, I will label all the vertical legs by the non-abelian object sigma. I also choose to label part of these horizontal edges that I denote by gamma I by sigma as well. Then only the gamma ijk edges are labeled by the abelian objects, and these will be effectively my degrees of freedom in my Hilbert space. So these states have one qubit on each vertex of a honeycomb lattice, basically. The Hamiltonian is constructed by fusing the abelian line to these fusion trees, and evaluating it gives precisely the same Hamiltonian that Kitaev wrote on in 2006 up to a unitary transformation. So this Hamiltonian is defined for qubits on a honeycomb lattice, and the nearest neighbor interaction between two qubits depends on the type of link between them, whether it's X-link, Y-link, or Z-link. Okay, now the symmetries of these models. So this model has a Z2 one-form symmetry, which has fermionic statistics, and this also then gives rise to mutually commuting plaquette operators. In the fusion surface model framework, these can be represented as abelian loops fused to the inside of a plaquette. Then Kitaev found that this model is exactly solvable via free fermions when the eigenvalues of all these plaquette operators are fixed to plus or minus 1. So that's why we know the phase diagram exactly. It's usually plotted for when the sum of the coupling constants is equal to 1. So this is why it has this triangular shape. In these green phases, one coupling constant dominates over the other two, and the model reduces to a toric coding perturbation theory. The phase in the middle is gapless, but it becomes chiral Ising topological order when time reversal symmetry is broken. So this type of topological order has characteristic gapless edge modes characterized by the chiral Ising conformal field theory propagating on the boundaries when the system is defined on an open manifold. Okay, the key takeaway from our previous paper is that if we now choose different inputs other than the Ising category, but keep the same form of the Hamiltonian, then we get generalizations of Kitaev's honeycomb model in the sense that these models will still have exact one-form symmetries as well as qualitatively similar phase diagrams, but they are no longer exactly solvable. Still, here's kind of like the schematic phase diagram that we found So when one coupling constant is large, one can do perturbation theory and show that the model reduces to an effective string net with a commuting projector Hamiltonian. At these red points, one coupling constant is 0 and the other two are equal. So here the system effectively simplifies to a stack of decoupled 1D anion chains, which are gatless. And so we expect that the phase in the middle should be qualitatively described by weakly coupled anion chains. And this is where we might have chiral topological order when the Hamiltonian explicitly breaks down reversal symmetry. Okay, so finally, I'm ready to give you kind of like the new results. So how can we construct these fusion surface models, which are dual to the ones that I just showed you? So basically, we just do the exact same thing that we did in 1+1d. We label these planar edges now by objects in the module category. And then we also, again, we get these potentially multidimensional fusion spaces at these vertices involving rho. So we can label these with basis vectors. But now the key difference to 1+1d is that these 2+1d diagrams involve a trivalent vertex where 3 objects of the module category meet. So this tells me that the module category must have its own tensor product. And this makes it a module tensor category. So module tensor categories over braided fusion categories can, in some sense, be seen as like a categorization of the module categories over fusion category statement. And they have been studied in the mathematical literature for a while. Sometimes they are also called B-enriched or B-central tensor categories. The Hamiltonian has then basically the same form as before. So again, we fuse an object labeled by we fuse a line labeled by an object in the braided fusion category to these fusion trees. But now, in order to compute this Hamiltonian explicitly, we need an additional set of F symbols, which are only well defined for module tensor categories because they involve this trivalent vertex here, where 3 objects of this module tensor category meet. So we didn't have these F symbols in the 1+1d case where we had module categories. We also need a half braiding phase between objects in M and objects in V. And I would expect that one can work out these additional F symbols and braiding phases from consistency equations similar to the pentagon and hexagon equation. Okay, and also the phase diagram I would expect for these kind of like extended fusion surface models, I would think it's pretty similar to the phase diagram I've showed you before. The key difference now is only that in these limits here, the string net should be characterized by the module tensor category.
Hi, I have a question about this phase diagram.
Yeah.
So in the last time you showed it, you said that the TO is always Z of B. I was wondering, well, what does B have to be such that that is what the TO is? Because that isn't the case for the Ising fusion category.
Yeah, like Ising, the problem with Ising is it's a bit special because I've basically fixed some of the horizontal edges to be some of my like planar edges, some of the degrees of freedom in the Hilbert space to be sigma. And the Hamiltonian doesn't change this because the Hamiltonian only consists of the abelian lines. So Ising is kind of like a special case. So we don't get basically Z of B here for Ising. We don't get an Ising string net, we just get a toric code.
Do you understand what the general statement is then?
Well, I guess the general statement is that for any fusion category which is not like Ising or Tambara Yamagami, we should have Z of B or more generally Z of M here.
Okay, thank you.
Thanks. Okay. Okay, so let's redo the example that I did in 1+1d, now in 2+1d. So this example is based on the rep S3 fusion category. And there are 2 ways to equip this category with braiding. We can either choose non-symmetric or symmetric braiding. And symmetric braiding means that the braiding phases are all real. And that's the braiding we have to choose here if we want to be able to have the trivial category VEC as a module tensor category over V. Okay, and then in this case, states in the Hilbert space look pretty similar to the 1D case. So all these red edges are labeled by the unique object in back and don't really contribute degrees of freedom. The fusion spaces, which involve rho, are two-dimensional, however, and so effectively we kind of get qubits at all of these gray vertices. And these qubits then effectively span a honeycomb lattice. The Hamiltonian has the same XXZ type interactions as before. So really the model we get is just the spin 1/2 XXZ model defined on a honeycomb lattice. And we know that this model has 0 form symmetries, in particular a U1 magnetization symmetry and a Z2 spin flip symmetry. It doesn't have any one form symmetries. And just as a side comment, we could also write the square lattice XXZ model in this fashion by simply changing the geometry a bit. So instead of having 2 vertical legs here, we could just have 1 vertical leg. And in this way, we could write the XXZ square lattice model also as a fusion surface model. Okay, and I will just flash some phase diagrams here because I think it's useful to make contact with physics. So it has been known for like a long time that at the isotropic point, these 2+1 dimension XXZ models have antiferromagnetic order when delta is larger than 0. And they should also have gapless Goldstone modes when delta is in this easy plane regime, because in this regime, the continuous U1 symmetry gets broken spontaneously. When one of these JX, JY, JZ coupling constants is large, then the model just enters into a trivially gapped phase with a unique ground state. And if one wants to find like the transition between these two phases explicitly, then one can turn to numerics. So for example, one can do infinite DMRG on a cylinder and plot the quantum correlations along the rung and along the infinite axis, as well as the second derivative of the ground state energy. And in particular here, we can see like a clear peak, and that's basically where the transition is happening. Okay. Now the model which is dual to this XXZ honeycomb model is, for example, the one which is constructed from the regular modular tensor category, so just rep S3. In this case, the degrees of freedom in my Hilbert space are objects in rep S3, and the Hilbert space is constrained. Unfortunately, in this case, I wasn't able to find a nice like Rydberg blockade type interpretation of this constrained Hilbert space as in 1+1d, but yeah. So we have a constrained Hilbert space, and we also know that the model has to have a one-form symmetry corresponding to objects in rep S3. And so it seems that the duality map we found effectively amounts to gauging this rep S3 one-form symmetry so that it becomes the S3 zero-form symmetry of the XXZ honeycomb model. Yeah, like determining the phase diagram of this fusion surface model is more difficult because of the constrained Hilbert space, because it has more degrees of freedom, so it didn't do any numerics here. However, when one of the coupling constants is large, we would expect it to reduce to a rep S3 string net. And yeah, but the phase in the middle here is less clear. But we know that because the 2+1d XXZ model was gapless when delta is in the easy plane regime, this phase should also be gapless for this model when it's in this regime for delta. So that's like one consequence we can get from the duality between these two models. Okay, then another example I looked at is constructed from 2 copies of the Ising category. So second copy has opposite braiding. This is what I'm denoting by the bar here. The states in the Hilbert space are constructed by fusing these, the states in the Hilbert space are constructed by labeling all these vertical legs by the sigma bar object, as well as some of these planar edges by the sigma bar object as well. So that's reminiscent of what we did for Kitao's honeycomb model, which was constructed from just one copy of the Ising category. then the degrees of freedom effectively live on these ijk edges here, and they are labeled by one of the 4 abelian objects. So effectively, the Hilbert space has 2 qubits at each vertex of a honeycomb lattice. Now, the Hamiltonian is constructed from fusing the abelian lines to my fusion tree. It has the same form as before, so I'm not writing it down again. Fusing this 0,1 line to the lattice gives me a Kita honeycomb model Hamiltonian which acts on the first layer of qubits, and fusing the 1,0 line gives me a Kita honeycomb model acting on the second layer of qubits. So that's these 2 terms. The 1,1 term then gives me a coupling between these 2 layers, and the coupling is just basically the product of the 2 local terms. So for example, if you look at an X-link, then we would have an XX interaction between 2 qubits in the first layer, and then an XX interaction between 2 qubits in the second layer. And then this here, the coupling is basically a product of 4 X operators. By construction, this model has 1Z2 symmetry in each layer, 1Z2 one-form symmetry in each layer individually. And in fact, at the isotropic point, this model has been written down before and studied numerically and analytically in a recent paper, simply for its interesting phase diagram. So not in the context of fusion surface models. But again, it's kind of interesting that we can recover all these models in the fusion surface framework. Okay, so here's the phase diagram of this model at the isotropic point. When the coupling delta is 0, then of course we only have 2 decoupled Kita honeycomb models in the Kepler space. When delta is small, then some perturbation theory and mean field analysis shows that effectively we get a chiral perturbation, and so we have kind of like 2 basically decoupled chiral Kita spin liquids. The topological order resulting from this is Ising times Ising bar topological order, and we would also expect gapless edge modes described by the full Ising conformal field theory. So these are non-chiral gapless edge modes. When delta is large, one can do perturbation theory and find that the model effectively reduces to a quantum dimer model defined on the Kagome lattice. And it is known that this Kagome lattice quantum dimer model has toric code topological order. So then a transition between these 2 phases should be an anion condensation type transition between this Ising times Ising bar topological order and the toric code topological order. And we expect it to be in the 3D Ising universality class. Okay, so what's the dual model for this? So one dual model we can construct is...
I have a question about that phase. So I have 2 questions. The first is, which anions are condensing here? And my other question is, can you understand the transitions in terms of the symmetries?
Okay, so the anion that's condensing here is basically the one bar anion in the Ising times Ising bar topological order. So this then gives me like the toric code topological order. In terms of, I'm not sure about the second question. So like, what do you mean by understanding it in terms of the symmetries?
Oh, can you understand it as some sort of spontaneous symmetry breaking transition of the one-form symmetries?
Oh, yeah, I mean, I guess you can interpret it in this way. I mean, of the kind of like of the one-form symmetry corresponding to the 1 bar anion.
Mm-hmm.
Yeah.
Okay, thanks.
Just to clarify, the 1 is the fermion in the Ising?
Yes, sorry.
Okay.
Yeah, I mean, like my notation basically says 0 for identity and 1 for the fermion. Yeah.
That's good, thank you.
Okay, so then basically we can get a dual model to this one by choosing just the 1 copy of the Ising category as a module tensor category over 2 copies of this Ising category. And in this case, basically the action of this braided fusion category on the module tensor category can be basically written down by just taking the tensor product of all single copy Ising objects. Okay, and yeah. So then states in the Hilbert space look like this. Now we have qubits located at these trivalent vertices because the fusion spaces here are two-dimensional, and we also have additional qubits located at certain links. The Hamiltonian we get has XXC type interactions between the qubits on the vertices, but it has basically kind of like ZZ and X type interactions for the qubits on the links. And it's also coupling like the link and the vertex qubits, as you can see here. So this motivated me to call the model XXC Ising model. And one can write down a Z2 one-form symmetry, which is conserved by this model, as well as an independent Z2 zero-form symmetry. Okay, so here's the phase diagram that I think should hold for this model. So when delta is small, one can do perturbation theory and find that these vertex qubits here freeze into two paramagnetic ground states, which spontaneously break the zero-form symmetry, the Z2 zero-form symmetry. The link qubits remain fluctuating, and they are governed by an effective toric Hamiltonian in perturbation theory. When delta is small, then this phase is kind of like more difficult to determine because I wasn't able to do like a perturbation theory argument here. However, since the XXC Ising model has both the Z2 zero form and the Z2 one form symmetry, it seems that it comes from the bilayer model by basically by gauging the diagonal Z2 one form symmetry in the bilayer model. And then this paper here on symmetry-enriched topological orders, following their arguments, I would expect that this phase here should be described by a symmetry-enriched toric code, because it follows from basically gauging the Z2 one-form symmetry in the Ising times Ising bar phase of the bilayer model. And then, because basically we expect toric code topological order on both sides of the transition is effectively just a Z2 zero-form symmetry breaking transition. And as such, we would also expect it to be described by the 3D Ising conformal theory. Okay. Yeah, so these are just some examples to give you a feeling of what kind of dualities we can realize in these fusion surface models. Now, finally, I want to say a few more comments about the symmetries of these extended fusion surface models. So far, everything has been quite straightforward and very close to the 1+1d case. The tricky bit in 2+1d is determining the symmetries of these dual fusion surface models mathematically, just from the data of M and B. So from a mathematical perspective, we would expect that the symmetry fusion 2 category of this model should be the Morita dual of the fusion 2 category mod B with respect to the module 2 category mod M. So this is just basically a categorified version of the 1+1d statement that that the symmetry category in 1+1d is the Morita dual of the fusion category with respect to the module category. Okay. Okay, and here by mod B, I'm just denoting the condensation completion of this braided fusion category. So this is a fusion 2 category whose objects correspond to algebras in B. And this this dual fusion 2 category has been explored in the mathematical literature, even though I would say it's still not like 100% worked out for all possible examples you could think of. Okay. Still, from the math literature, I think there are at least two key takeaways that I found. So one takeaway is that the one-form symmetries, which should correspond to one morphisms in this dual fusion 2 category, are labeled by objects in the Drinfeld center of M that braid trivially with B. And the intuition for this is that we want this symmetry line to deform freely across the picture here. So in particular, we want to be able to slide it past these blue legs, which are labeled by objects in B. And so that's why we want them to braid trivially with B. The difficult part is determining the zero-form symmetries. So their existence depends on a certain functor. This functor maps from the braided fusion category into the Drinfeld center of M, and its existence is guaranteed by the structure of a modular tensor category. If this functor is fully faithful, meaning that B can be embedded into Z of M, then the model will only have one-form symmetries, no zero-form symmetries. And this assumption was made in some recent papers on string nets living on the surfaces of 3+1d Walker-Wong models. And basically, these string nets on Walker-Wong surfaces look very similar to the fusion surface models, because you can think of extending these vertical legs into the bulk of a 3+1d Walker-Wong model. But we don't have to make this fully faithfulness assumption. And in fact, if the functor is not fully faithful, then we get models which have independent zero-form symmetries. So that's, for example, what you saw in the rep S3 case, where the XXC model had just an S3 zero-form symmetry. But writing down the zero-form symmetries just from the data of B and M, and also determining their lattice action precisely, is still kind of like left for future work. So I wasn't able to figure this out in all detail.
Question?
Yeah.
So maybe you already said it. How do you extract this functor from within this model?
So the functor exists for any modular tensor category over a braided fusion category. In fact, sometimes this is used as like a definition of a modular tensor category over a braided fusion category.
Okay, but in this model, how do you concretely like compute this?
It's a good question. I mean, I guess it wouldn't. I mean, it doesn't really depend on my lattice model, right? It only kind of like depends on the categories. And I would expect that maybe thinking about kind of like commutative algebra objects and constructing kind of like module functors from them, I should be able to get this functor explicitly. But I haven't really thought much about that.
I see. There may not be a unique functor, right, from B to Z.
Yeah, that could be. Yeah, I don't know if it's unique. Probably not. Yeah.
I see. Thanks.
Hey, Luisa. This is Meng. So, your F is a braided functor, braided monoidal functor.
Yes, it's a braided functor. Yeah.
And B is not. B is also braided, right?
Yes.
So I guess there's something having to do with the identity in the double of M that might tell you what the zero form symmetry is. Objects that are mapped to identity is that what you mean by not faithful?
So what I mean, okay, so what I mean by faithful is that basically every object in B has a corresponding object in the Drinfeld center of M. So there's kind of like a mapping between these. And if this mapping like doesn't exist, then like this Morita dual fusion 2 category has like multiple components which are not connected.
Okay.
Yeah. Thanks.
I see. Thank you.
Okay, so basically that was already it. So we saw that we can construct dual fusion surface models very similar as dual anion chains by choosing different modular tensor categories over the braided fusion categories. And this new word module tensor instead of just module category is necessary so that we can incorporate these like trivalent vertices where 3 objects of this module category meet. And it's also necessary to make it consistent with the braiding. Another important point is that when this module tensor category is no longer the same as the braided fusion categories, then the models can have both zero form and one form symmetries. And so this makes them candidates for symmetry-enriched topological order. And another point which I like is that this basically extended framework allows us to cast more familiar models like the XXC, honeycomb, or square lattice models into the fusion surface model framework. And I mean, there's several future directions I could think of, so it would be interesting to look into models which realize topological phases enriched by potentially non-invertible symmetries, because these would be outside the usual G-cross braided framework. It will also be interesting to see if we can get self-dual fusion surface models in this way. And finally, it is known that many 1+1d dualities can be implemented efficiently with adaptive or sequential quantum circuits. So this raises the question if the same also applies to these 2+1d dualities. Okay.
Thank you, Luisa. So are there any questions? Please feel free to unmute yourself and ask directly.
Can I ask a question about the comment on the symmetry-enriched topological order? Here, what is the I mean that if you have some functor, fiber functor, generalized fiber functor from the category B to some target category, what is the symmetry of this phase?
So as I said, so I don't have like a complete understanding of what the symmetry fusion 2 category is in any possible case. So
yeah, maybe I can just fix all the not fusion 2 categories, just all the fusion 1 category. So what is the ACT phase in this case? Like given a fusion category symmetry. Use the fiber functor description.
Okay, I'm not super familiar with like fiber functor descriptions for symmetry and topological order.
Okay.
Yeah, I'm sorry.
It's okay. It's okay. Thank you.
Can I ask a question? Sorry, I still can't switch on my video for some reason. Thanks for a nice talk. So one question is, in this way you're describing these models, how easy is it to do numerics on these? Which on the anion chain you can of course also do, but you always have to do sort of impose this constraint by hand. So is this a similar sort of problem in these models, or is it, can you find usually nice sort of tensor product realizations?
No, I would expect that, like, I mean, there are certainly like examples of tensor product Hilbert spaces like the XXC model, but I think that's basically kind of like an outlier. So like in general, I would expect a constrained Hilbert space. And then I would have to impose this in some way to DMRG or PEPs. Right. So yeah, it would be like, as difficult as in 1+1d.
And then another question is, so you looked at a lot of models which are essentially so easing type transitions with Z2. Surely you could also look at, say, Z3, and then we actually don't know so much about what we would expect as the critical model. So actually it's an interesting question to explore, maybe, feed into this whole system a Z3 symmetric, fusion.
You mean something like a bilayer model with Z3 Tambara Yamagami Z3?
Yes, and so now can you get something interesting about using numerics now, some information about this transition.
I see.
That Z3 symmetric. It's just sort of thing that, if you actually look into 3D CFTs with, finite symmetries, it's not as canonical what you would actually be looking for as I think in 1+1d, where you have like 3-state pods or other, for any ZN symmetry.
I see. Okay, yeah, that sounds interesting. Okay.
Okay, thanks.
Thanks.
So I have a couple of questions. So did I understand correctly that in some models you have control over the symmetry, right? Like you said in some specific case.
Yeah, so I would say that like if this functor here is fully faithful, then we only have one-form symmetries. And the one-form symmetries should be described by objects in the Dirichlet center of M that braid trivially with B.
I see.
Yeah.
And so this has a non-anomalous one-form symmetry given by B. So, so there's nothing that braids with B in this symmetry.
Yeah.
So, but the symmetry broken phase would be Z of M, basically. The B symmetry broken phase.
I'm not sure. Okay, I mean, what I mean by this is just it's like the subset of objects in M that braid trivially with B. But I'm not sure if it makes sense to say that it breaks the symmetry. I don't know.
Yeah. What I mean to say is that Z of M is a modular tensor category, right? But the fusion, the symmetry is not the full modular tensor category. It's only the subcategory that braids trivially with M. With B. But then one can deform this model to a phase where the B symmetry is broken such that the phase.
I see.
It realizes the Z of M as a phase of this model, which is the B
now I see what you
SSB.
mean.
Yeah.
Okay, yeah, I think that should be possible in some way. Yeah.
Another unrelated question is: do you have an understanding of how to look at twisted sectors in these models?
Like I thought a bit about this, but then I kind of like abandoned it because it seemed more involved. Because I would have to look into kind of like twists coming from like zero form symmetries and then twists coming from one form symmetries and how they interact. And yeah, so I didn't look into this further. Yeah.
I see. And is there an understanding of like, so if we want to construct some specific symmetry category which involves zero form symmetry and some one form symmetry with a symmetry fractionalization, how to constructively choose B and M?
I think we're working on this, Apurv, no?
Yes, but I mean,
it's a trick question, I think.
Yeah, it's a good question. Yeah, no, I don't have an answer to this. I don't know how I would constructively get these phases. Yeah, and no, yeah.
Okay, thank you.
Thanks.
So if there are no more questions, let's thank Luisa.